Good evening, everyone. Am I audible?
Yes, ma'am.
Okay. Okay, let's wait for 5 minutes so others can join. Then I'll start. Okay. let's start this session. So this is the second problem solving session for the course Real Analysis 2, and in the last session we have discussed about metric spaces, norm spaces and equivalent metric spaces, right? So in this session I'll start with subspace matrix topology. Okay, so suppose xd is a metric space. Metric space, this is short for metric space. Okay, so suppose xd is a metric space and y be a subset of x, then y with this metric d restricted to y, since y is a subset, is also a metric space, right? It is also a metric space and it is a subspace metric space. Okay, now the question is the open balls of x, how the open balls of y in this metric looks like, right? So the question is, if b, suppose y belongs to y, since y is a subset of x, y also belongs to x, so b y r is a ball, open ball in x, right? Now how does the open ball centered at y with respect to this metric looks like? So since it is an open ball, so BYR intersection y is also open, it is an open ball in y, right? Now the question is, does every open ball in y looks like this one? Means every open ball of y is a intersection of an open ball of x intersection y. The question is this. So now we'll see that b y r intersection y, it is what? It is this set, this is all those x belongs to x, because BYR is a ball, this is BD I am writing, this means D yx less than r, it is BYR intersection y. Now here x belongs to x and intersection y means this is all those x belongs to y such that D yx is less than r, right? Now it is a subset of y, so it is nothing but b all those x belongs to y such that dy yx. Now since all those x belongs to x, this is dy less than r and it is nothing but b dy yr, right? This means every open ball of y are nothing but the intersection of the open balls of x with y, right? So this means the open balls of y are precisely the intersection of the open balls of x whose center are in Y, right? Whose center are in Y with Y. Intersection of the open balls of X with Y, right? So this is about open balls. Now open sets are generated by open balls, so all the open sets of Y are precisely the intersection of open set of X with Y, right? So this is also true for open sets, and you can prove that. This is a theorem. I'll say theorem 1, suppose. So let Y be a of a metric space. This is short for metric space, okay? Metric space xt. Then U subset of Y is open in Y with dy. Dy means the metric restricted to Y. Dy if and only if U equals to V intersection Y, where this V for some open set B in xt. Okay. So every open subset, open set of Y is nothing but intersection of a open set in X with Y, right? Okay, so let's see some examples to understand this. So RD, so R, I am taking du. Du means the usual metric in R, that is the Euclidean metric, right? So it is a metric space, and take this subset. So here this subset I am taking 0, 1, right? So I di restricted to I is a subspace metric space, right? Now what are the open sets or open balls of I, right? So in R, every open set, every open ball looks like some AB, right? So in R, open balls of R with respect to this usual metric du is of the form AB, right? In R, suppose this is R. Every open ball, I am not saying open sets. Open sets can be union of AB in union CD, right? Some open balls around some point. This is some interval, right? So every open ball looks like some open interval AB. Now what about the open balls of I? So I is 0, 1, right? So every open balls of I will be, so open balls of I is what? This open balls of R intersection I, right? Now what is this set? AB intersection I. So AB can be anything. A can be less than 0, B can be greater than 1, like this. So there must be some cases. So if A less than 0, less than B, less equals to 1, less equals to 1. So What about this case? So AB is an open interval and I is 0 1 closed interval. So if A less than 0 means A is somewhere here and 1 is B is here, right? So this intersection will be 0 B, right? And if 0 less than A less than 1 less than B, then it will be A1, right? And if 0 less than A less than B less than 1, A, B are both contained in 0 1, then it will be only AB. And if A less than B less equals to 0 or 1 less equals to A less than B, then it will be phi, right? A, B both are outside 0 1, so it will be phi. And if A less than 0 less than 1 less than B, then it will be 0 1. So it is nothing but I, right? It is I. So open balls of I with respect to this metric di will looks like this one, right? Now see this kind of balls, this 0 B, A1 and 0 1, no 0 1 is the whole set. So this kind of balls, these are not open in R, right? This subset, these are not open in R, but they are open, in I di, right? In subspace metric they are open, but they are not open in the whole space. Okay, so let's see the next example. So similarly here R with usual metric, okay, and here we are taking the subset n, which is the natural numbers, okay, the set of all natural numbers. So n subset of R. Now what are the open balls of n? Okay, this is the question. So this is n, means starting from 1 2 3 like this. So the open balls are intersection AB intersection n, right? This is the open balls of n are of this form. Now if we take AB to be some n minus 1 by 3 n plus 1 by 3, right, where n belongs to n. So if we take this kind of intervals, then this interval intersection n will be the singleton element n, right? So for each n we are taking this interval n minus 1 by 3 to n plus 1 by 3. So intersection of this interval with n is only n, right? So each singleton element in n are open. So every open ball is the singleton element, right? So this means what? So each singleton n is open ball in n, right? See, singletons are not open in R, but singletons are open in this N with subspace metric, right? And since singletons are open, this means every subset of N is open, right? Because every subset is the union of these singletons, and union of open balls, arbitrary union of open balls are open. So every subset of N is open. So this means every subset of N is open in N, right? And same thing happens for Z, the set of all integers, right? So here we see that if we take N with district metric, and in district metric we have seen that singletons are open, right? So N, if we take D star, which is the district metric, so it is the discrete metric, then we have seen that if singletons are open and every subset is open then. So they generate the same topology, right? Topology means the collection of all open sets, and since singletons are open in both cases, means N D star and N with du dn, that is the usual metric restricted to N. So they both generate the same topology, right? Okay. So in the last session we have discussed about equivalent matrices, metric spaces, right? And I have given a sufficient condition or necessary condition if two metrics are equivalent or not. Now there is a result, which is this theorem 2, I think. So it is a necessary and sufficient condition for two metrics to be equivalent. So two metrics D1 and D2 on a non-empty set X are equivalent if and only if for each x belongs to x and each sequence xn in x, this condition is satisfied. This limit n tends to infinity xn equals to x in x d1 implies vice versa goes to xn equals to x in x d2, right? This is a sequential criteria and this is necessary sufficient condition for two metrics to be equivalent. So it says if xn converges to x in the metric d1, then xn must converge to x in d2, right? And similar and vice versa. Okay, so I'm not going to the proof. You can check any proof for this proof, and this is easy. You can also do it by your own. Okay, so I will use this theorem to prove this xd and xd1, where this d1 is d by 1 minus d. This xd and xd1 are equivalent, right? So in the last session we have already shown that these two are equivalent, these two metrics, and now we'll show this by this theorem. Okay, so it is clear that d1 xy, d1 is, this means d1 xy equals to dxy by 1 plus dxy. To show d1 and d and d1 are equivalent, means they generate the same topology. Okay, so we'll prove this using this theorem too. So we have to show that if xn, so let xn be a sequence in, suppose first be a sequence in xt, sequence in x such that xn converges to x in xd, right? In d, xn converges to x. Now we have to show that xn converges to x in x d1, right? So this means what? This means d of xn x goes to 0 as n goes to infinity, right? Now to show d1 xn x goes to 0 as n goes to infinity, right? Now d1 xy is what? d1 xy is dxy by 1 plus dxy. So it is always less than dxy, right? So d1 xn x is less than d of xn x, and which goes to 0 as n goes to infinity. So d1 xn x must go to 0 as n goes to infinity. So the first part is clear. So this one. So this part is clear. Now we have to show the other one. Means, now suppose for the converse, suppose xn converges to x in x d1, right? So this means d1 xn x goes to 0 as n goes to infinity. Now you have to show that, to show d of xn s goes to 0 as n tends to infinity, right? That we have to show. Now d1 xn x goes to 0 means what? Means what? Given epsilon greater than 0 there as n goes to infinity, means given any epsilon greater than 0 there exists an natural number n such that d1 xn x is less than epsilon by 1 plus epsilon for all n greater or equals to this n, right? We could have take this d1 xn x less than epsilon, but I am taking epsilon by 1 plus epsilon because it will ease the proof. Okay, so this means d xn x by 1 plus d is less than epsilon by 1 plus epsilon. This means d of xn s is less than epsilon, right? For all n greater or equals to n. And this implies xn converges to x as n tends to infinity, right? So by theorem 2 then by theorem 2 d and d1 are equivalent. Right? Okay. Okay, let's go to the next problem. Okay. Let's take R with the usual metric. Is the usual metric, and R with the discrete metric. This is the So the question is, this D and D star are equivalent or not? Right? So take this sequence. So by theorem 2 we'll prove that these two are not equivalent. Okay. So we have to think of a sequence which converges to some du suppose, and does not converges in D star. Like, so take xn to be 1 by n. Right? So this sequence xn converges to xn converges to 0 in du in x du, right? Because it is the usual metric. So 1 by n goes to 0 as n tends to infinity. So xn converges to 0 in the usual metric. Now, does it converges to 0 in discrete metric?
No, ma'am.
Why?
Because 0 is not included.
0 is included there. 0 is belongs to R. 0 is there. Converges in R or not? R is the whole space. I am taking a sequence. I am not taking xn are the all the set of x. The set is the whole R. From R I am taking a sequence 1 by n. So does it converge in R by the metric D star? See, if xn converges to 0 means what? In the usual metric, a sequence converges to some point means if we take any open ball, any neighborhood of that point, suppose 0, and I am taking any neighborhood, epsilon minus epsilon to plus epsilon. This means, suppose xn converges to 0. This means what? This means every neighborhood of 0 must contain xn. This means one second. This means there exists some n, a natural number, such that a neighborhood, suppose minus epsilon to plus epsilon, or I can write n epsilon 0, a neighborhood of 0 with radius epsilon, right? So every neighborhood will contain xn for all n greater equals to n. After some n, all the terms of this sequence must belong to that neighborhood. This is what this means, right? A sequence converges to some point means a sequence converges to A means every neighborhood of A This is a minus epsilon, this is a plus epsilon, contains all the points xn after some n. From x1, x2 to xn must be outside, but after that n, all the terms of this sequence must belong to that neighborhood. This is what convergence means. Okay. Now since in usual metric, if this is 0, a neighborhood of 0 means an open interval of 0, right, in usual metric. So this is minus epsilon to plus epsilon, a open neighborhood. This is a neighborhood, this is open interval. So after and our sequence is what, 1 by n, right? So after some n, all the values of 1 by n will be in that neighborhood, right? So this is why xn converges to 0 in usual metric. This is this line. So xn converges to 0 in usual metric. But we'll see that xn does not converge to 0 in discrete metric. Why? So take any open ball around 0, right? Suppose b half, or I can write b d star, means in district metric 0 half, 0 with radius half, right? So what is this set in discrete metric? This means what? This means these all those x belongs to R such that d star 0 x is less than half, right? Now d star x is what? This is a discrete metric, so either it is 0 or 1, right? If x is not 0, it is 1, and if x is 0, then it is 0, less than half. So it is only this singleton set 0, right? So b d star, a open ball of 0 in discrete metric, contains only 0, no points of this sequence xn. So 0 can never be a limit point of this sequence xn, right? So xn does not converge to 0 in R d star. This clear, right? So with respect to usual metric, it converges to 0, and in d star it does not converge. So xn does not converge to 0. So then by theorem 2 says what? Theorem 2 says, if in d1 xn converges to x, and this implies it converges in d2, then they are equivalent. So it is not equivalent, right? So this means du and d star are not equivalent in R, right? Okay. Okay, let's move forward. Okay, now we'll discuss about Cauchy sequence. So we'll discuss about completeness and compactness in this session. Okay, so first is Cauchy sequence. So Cauchy sequence is what? A sequence xn in a metric space xt is said to be Cauchy sequence in x if given epsilon greater than 0, there exists a natural number n such that d xn xm less than epsilon for all m n greater equals to n, right? This means what? This means d xn xm, the distance between this xn xm goes to 0 as mn both goes to infinity, right? This is the definition of Cauchy sequence. Now here we'll take this one, this set. Suppose now x is our 1 by n, right? Here x is not r, x is only this sets 1 by n, where n belongs to x, right? Now we'll consider x with usual metric and x with discrete metric, right? And we'll verify if this sequence xn 1 by n converges in these two metric spaces, right? So sorry, not convergence, if this sequence is Cauchy or not in these two metric spaces. So what about the usual metric space? In du, in the usual metric space, this is usual metric space and this is discrete. So we have already seen that in usual metric 1 by n converges to 0 in du, right? This means du 1 by n 0 goes to infinity as n goes to infinity, as n goes to infinity, right? So since it is convergent, and convergent always means Cauchy, right? So this means 1 by n is Cauchy. Cauchy in x du. Right? Now, is it Cauchy in discrete metric space? Cauchy means what? D star, we have to find if D star 1 by n goes to 0, if this goes to 0 as mn goes to infinity, right? Now, is it true? So this is not possible, right? If m is not equals to n, then d star 1 by n is 1, right? So this can never go to 0, right? So this does not go to 0 as mn goes to infinity, right? For all m not equals to n. If m equals to n, then it is 0. But whenever m not equals to n, then it is giving the value 1. So it never goes to 0. So this means 1 by n is not Cauchy in x d star, right? See, in discrete metric space, a sequence will be Cauchy if and only if it is a constant sequence. Otherwise it will never be Cauchy. It has to be a constant sequence. Otherwise the difference between two points will be 1, right? So in the remark I will write that the the Cauchy sequences in a discrete metric space are the constant sequences. Okay. Okay, so we have defined Cauchy sequences. Now we'll define completeness. So complete metric space. So a metric space is called complete if every Cauchy sequence is convergent. A metric space xt is said to be complete if every Cauchy sequence in that space X converges to some point in X. Converges to some point in X. Right? So as an example, we'll see some complete and incomplete metric spaces. So the first one is R with usual metric. So we'll see that R with usual metric will be complete. I'm not giving the proof. You can check any book for reference. And also this 0, 1 with the same metric, usual metric, is complete. Right. Now for the second one, if we take X to be, the whole space is open 0, closed 1. Right. And D is the usual metric. So is it complete? This is an easy question. We have already seen the sequence 1 by n, right? So is it complete? This is an easy question, you have to answer. Okay, so this metric space is not complete. Why? Because this sequence 1 by n, this will be Cauchy because it is converging to 0 means it is Cauchy, right? Because convergent always means Cauchy. So xn is Cauchy, but it converges to a point which is not in the whole space X, right? That's why it is Cauchy but not convergent. So this xn is Cauchy but not convergent in X, right? So X is not complete. Okay. So what about the discrete metric? Is it complete? So X be any metric space with D star, okay, and D star is the discrete metric. So complete means every Cauchy sequence must converge, right? And in remark I have written that every Cauchy sequence of a discrete metric space are constant sequences, right? And constant sequence always converge, right? So every Cauchy sequence in discrete metric space always converge. So X, any metric space with complete discrete metric space converges. Sorry, is complete, right? So since every Cauchy sequence in XD star is constant sequence, therefore every Cauchy sequence in XD D star is convergent. So X D star is complete. So X with discrete metric, it is always a complete metric space, right? Okay. So first we have taken this R with usual metric and 0 1 with usual metric, both are complete. And in second we have taken open 0 closed 1 with usual metric, which is not complete. And in third we have taken X, any metric space with discrete metric is always complete, right? Now we'll take this metric space, which is this CAB, which is the function space, is all those functions from this AB to R real value continuous function, right? And the metric is DFG. The element points are functions. So DFG is defined by maximum of T belongs to AB modulus of Ft minus Gt. Okay. So CAB with this metric D is a complete metric space. It's a complete metric space. Okay. This will prove right now. Okay. So this is not a short proof, but this proof uses a lot of real analysis. Okay. Okay, so let's start this proof. So yes,
Ma'am, will the recording of this session be available to us for watching later?
yes, I will upload this in YouTube, and I will share the link. But that doesn't mean you will not be attending this class.
Yes, ma'am.
You can ask any question here. In recordings you can see for later, but you have any doubt here you can ask me. Okay.
Okay, ma'am.
Okay. So so we have to prove this is complete, right? So this means we have to take a Cauchy sequence and we have to show that this Cauchy sequence is convergent, right? So first take a Cauchy sequence. So let Fn means every element is a function, right? So Fn be any Cauchy sequence in CAB, right? So what is this sequence? This is actually f1, f2, like this, right? Each are functions. So it is Cauchy. So given by definition of Cauchy sequence, given epsilon greater than 0, there exists some natural number n such that the distance between fn and fm is less than epsilon for all, and the distance is nothing but this maximum of fnt minus fmt is less than epsilon for all n greater mn greater equals to this n, right? This from the definition of Cauchy sequence. Now fix any t equals to t naught belongs to this a, right? For now maximum value, this maximum value here, this line, this maximum of this modulus is less than epsilon, right? So each value is less than epsilon. For each t, this value will be less than epsilon. So now we have fixed t naught. So for this t naught also, this implies fn t naught minus fm t naught is less than epsilon, right? For all mn belongs to mn greater than n equals to n, right? For some t, I have fixed t, this t naught can be arbitrary point, right? Now this means what? This means the sequence fn is a function, but fn t naught, it is a point in real number, right? So this implies the sequence f1 t naught, f2 t naught, and so on is Cauchy in R, right? Because the nth term of this sequence is what? Fn t naught, and mth term is fm t naught, right? So nth term minus this line, this line implies this sequence of real numbers, this is Cauchy in R, right? So it is clear, right? So this sequence is Cauchy in R, and R is complete, right? And R is complete. So this implies this sequence must converge, right? This is a Cauchy sequence and R is complete. So this sequence is converges. So this sequence means this fn t naught, this sequence is convergent, right? So let it converges to some point, let fn t naught converges to some f t naught, right? As n tends to infinity, as n tends to infinity. So what we see that for each t naught we have chosen fixed t naught arbitrary from AB, right? So for each t naught I am getting a point f t naught, right? So this fn means what? I am writing this for each t in AB we can associate a real number ft, right? For each t naught I am getting ft naught, right? So this means what? This means fn, this sequence fn converges to f pointwise, this is the definition of pointwise, right? Fn converges to Fn pointwise means Fnt, this sequence of real number Fnt converges to Ft for each t, right? So Fn converges to F pointwise. Now we'll show that what we have to show. We have to show that this function where it is converges must belongs to CAB, right? Then we can say that this is complete. This is a Cauchy sequence, Fn is a Cauchy sequence. We have to show that it is convergent. So to show this, so we have to show now that Fn converges to F uniformly, and this function F must belongs to this CAB, right? Means F has to be continuous also. So till now we have found that Fn converges to F pointwise, right? Now from the from this line I will get what this line is, what dn Fn and dn Fn, which is maximum of this is less than epsilon for all mn greater than n, right? This we already have. Now letting n tends to infinity, will get here I am letting n tends to infinity, right? So pointwise means what? This is Fnt converges to Ft for each t. So this Fnt here, this Fnt will go to Ft. So from here we will get maximum of Fmt was like this one, and Fnt goes to Ft, right? This is less than epsilon for all mn greater equals to n. Letting n tends to infinity, we are getting this. Now this already means Fn goes to F uniformly, right? Because the maximum value of Fnt and Ft less than epsilon. Oh sorry, here since I have taken n tends to infinity, this is for all m greater equals to n, right? So this implies this Fn converges to F uniformly. But why this uniform convergence is required? We have already found that it is converges pointwise, right? But why we need uniform? Because if Fn converges to F uniformly and all these Fn's are continuous, then we will have F is also continuous. This is a result in sequence of functions, right? In real analysis you can check. So since Fn converges to F uniformly, and
Ma'am,
yes,
ma'am, do we need to prove continuity also?
yes, because F has to be continuous, right? If we have to show that this Cauchy sequence must converges, right? And all the Cauchy sequence we have taken from CAB. So if it converges, the converging function must belongs to the space CAB, right? So F needs to be continuous to prove completeness. Okay. So for this we have shown Fn converges to F uniformly, right? And since each Fn is continuous, F will also be continuous. Will be continuous. Right. For this line, we need the uniform convergence. Right? Because you will see in the real analysis, you have seen that if it converges pointwise and each Fn is continuous, it does not mean the pointwise convergent function f will also be continuous. The convergence must be uniform convergence. Okay, so we see that what our fn was Cauchy, this fn was Cauchy sequence in CAB, and fn converges to f, and this f also belongs to CAB, means f is also continuous. This implies CAB is complete, right? If you have any doubt now, you can ask. Okay, so you have proved CAB is complete. Okay, next we'll see a result which gives a necessary and sufficient condition for completeness. Okay. So this is maybe theorem 3, I guess. So let xt be a complete metric space. Complete metric space, and Y is a subspace. Y be a subspace metric subspace. Space of X. Okay. Now when will be X, Y will be complete, right? Now every subspace is not complete. Okay, because R was complete and open 0 closed 1, this interval was not complete, right? So this Y will be complete, then Y with subspace metric, Y with subspace metric means this dy is complete if and only if it is closed in X. If that subspace is closed in the whole space, then it will be complete. Okay. So let's see a question. Now, is Q complete? So is Q, the set of all rationals are complete? No, right? Because it is not closed in R. R is complete, the whole space R is complete. Q with the usual metric. I have to mention. Sorry. Q. So this is the wrong question actually. Suppose R du is complete, right? Now the question is Q with this du is complete? Then the answer is no, because Q with discrete metric will be complete. Any metric space with discrete any metric space means with this discrete metric will be complete, right? So with respect to this metric, it will not be complete. Right? Similarly, R minus Q, set of all irrational with this metric, is also not complete. Why? Because it is not closed in R. It is not closed in the whole space. So that's why it is not complete. Okay. So let's prove this theorem. Okay, I think. Okay, so this is an easy proof. You can try it. Okay, so I am not going to the proof. So now Q is not complete. Okay, but Q bar, we see that this Q closure is R, which is complete. Right. Now, does this occurs for every subspace? Means this is every subspace. Every subspace. Every incomplete metric subspace contained in some subspace so Q is not complete, but Q is contained in, but Q bar is complete, right? Means Q is dense in R, in a complete metric space, right? Similarly, this 0 1, this 0 1 open 0 R, it is not complete because it is not closed in R, right? But 0 1 is contained in Q such that the closure of this Q is dense in R, the whole metric space, right? Q and Q bar is R, right? So the question is, does every incomplete metric space, incomplete, this is incomplete 0 1, is contained in some subspace, this here, this is Q, which is dense in the whole original space, right? Now, does this happens to every incomplete metric space? This is the question, right? From this question arises the definition or concept of completion of a metric space. If it is incomplete, how we can complete this, right? So first we need the definition of isometry. This is a function. So isometry means it preserves the metric, right? It preserves the distance. So let x d1 and y d2 are two metric spaces, right? Then a bijection means it is 1 1 and onto, right? A bijection f from x d1 to y d2 is said to be an isometry if for any AB belongs to X, the distance between AB in the domain is equals to the distance between the images in the codomain, right? Means it preserves the distance. Okay, then we'll say that it is an isometry, right? So example of isometry is the identity mapping. So identity mapping always preserves the distance. Means identity mapping from xd1 to xd1. Means identity example, the metric has to be same. So identity mapping I from xd1 to xd1, right? This is clear. Okay, now I'll give the definition of completion. So so completion means let xd be a metric space. Let xd be a metric space. Okay. And y d1 is said to be a completion of xd if xd is isometric with the dense yd1. yd1 will be called a completion of xd if xd is isometric with a dense subspace of yd1. That is, in another words, means there exists an isometry f from xd to its image fxd1 such that fx is dense in y, fx bar is y. Okay, so this actually means what? Suppose this is our x, okay, this is x with du, right? Now yd star or yd1 will be called a completion of this xd if the image under image, suppose this is an isometry f and its image, suppose this one, this is fx is dense in y, right? So this xd is isometric to this portion, this is fx, this portion which is dense in y, right? So fx bar is y. Then we'll call this y d1 a completion of x, like q, the set of all rational numbers. The completion of q is r, right? So q is not complete, and a completion of q is r, because why here what is the isometry here? The isometry here is the identity mapping, right? Because I from q to q, identity, this is identity. So identity is always isometry. So the image of I, that is iq bar, we have fx bar, that is iq bar, which is the q bar, is R, right? So R is a completion of Q. And similarly, R will also be a completion of R minus Q, all the irrational numbers, right? And if the space is complete, then the completion will be the space itself, right? So every complete metric space is a completion of itself under the identity mapping, right? And a theorem.
Ma'am,
Yes.
ma'am, you said that XD is isometric with a dense subspace of YD1. Ma'am, actually, I want to ask this statement in terms of this example of rational number that you gave in
Yes.
first example.
Yes. So Q is incomplete, right? And
Yes, ma'am.
R, I am telling R is that space Q has to be isometric with a dense subspace of R, right?
Yes, ma'am.
So Q is isometric with Q. Here, by identity, I am showing that Q is isometric with Q, and Q is dense in R, right? So by identity here, identity is isometric and the dense subspace is Q. Q is dense in R. So completion of Q is R. Completion is the whole space. Okay. So is it clear now?
Yes, ma'am.
Okay. And if the metric is complete, then the completion is itself. Okay. So a theorem says that every metric space has a completion and any two completion are isometric. So I am not going to the proof, but I am writing the theorem.
Ma'am, is this concept true for irrational numbers also?
Yes, because here the isometric, the function I am taking is identity. So for R minus Q, I is R minus Q to R minus Q, right? So the image of R minus Q is dense in R. So the image of this function I am taking, the isometry, has to be dense in the space, right? So it depends on the mapping, the isometry. So isometry here is I. So R minus Q goes to R minus Q, and R minus Q is dense in R. So the completion of R minus Q is also R. Okay? Okay, so it may be theorem, I don't know, theorem 4. These proofs are not easy for this completion, so you have to check the books for this. Okay, so it says every metric space has a completion, and this is a completion theorem, and any two completions of a metric space are isometric. Okay. Okay, now we'll discuss about compactness of a metric space. So, so compact metric spaces. So, a metric space xt is said to be compact if every open cover of X has finite subcover. Okay, this is the general definition. If every open cover of X has a finite subcover. Now, open cover means what? Open cover means a collection of open sets, and union of these open sets contains this X, right? So, this open cover means open cover of X means it is a collection. So, suppose this U alpha is a collection of open sets. U is open such that X is contained in union of this. Sorry, this is suppose U alpha, where alpha belongs to this lambda. Lambda can be any number, means countable, uncountable, finite, anything. So union of this U alpha belongs to lambda. So then we'll say that this U alpha, this U alpha is an open cover of X, right? So you see that this compactness, the definition of compactness depends on open covers, right? And open covers depends on open covers means it depends on open sets, and open sets generate the topology. So this compactness is a topological property, right? So means compactness is a topological property. Right? Because it depends on open sets, and it is also a metric property. Means if two metrics are equivalent, then if it is compact, if x d1 is compact, then x d2 will also be compact, right? I'm writing this also. It is a metric property. That is, if d1 d2 are topologically equivalent, then x d1 is compact if and only if x d2 is compact. This is a metric property also. Okay, let's see some examples. So
Ma'am?
Yes.
Ma'am, I often get confused when I study topology. So I often get confused with open cover and open base.
Open race.
Open cover and open base.
open base, open balls or open base, I don't understand.
Ma'am, base is actually a collection of those open sets whose union gives the whole
Okay,
topological
base
space.
is comes from linear algebra, right? Base, subspace, right? Basis means basis, right? Okay.
Yes, ma'am.
Here open base means what? Open base means open balls. Open balls generate the open sets. The minimum is open balls, right? Open set is what? Open set is the union of these open balls. Open balls generate open set, and open sets generate this topology, right? The base, you are telling the base are actually these balls. This is the smallest open sets, right? So balls may be different for metric spaces, but the collection of open sets may be same. For we have seen that for n with usual metric and n with discrete metric, the metrics are different, but the topology is same. The topology means the collection of open sets are same, right? The distance may be different. Distance are different, but the open sets may be different. In the last session we have seen that in R2, with norm 1, it is the open balls are uh, this disk, and in norm 2, norm 2 open balls were disk, and norm 2 and norm 1 it was this squares. These open balls are squares, right? And norm 3 it was something in between this, right? And norm infinity, for norm infinity it was this this one. So all the open balls here are different for different metrics or different norms, right? But the topology was same. But the open sets may be different. The open balls here are circles, disc, here the squares, but they generate the same topology. We have seen that all these norms are equivalent in R2 or Rn. Okay. Okay, so let's. So we are doing compactness. So now, if the set is finite, then it is compact, right? So every finite subset of any metric space is compact, right? We'll just take finite subcover. Every open cover has finite subcover, so it is compact. Now what about R? So is R compact? So R is not compact. Why? So we have to, there must be some open cover which does not have finite subcover, right? So take this open cover. This U is minus n to plus n, where n belongs to n, right? Now union of these intervals covers the whole R, right? So this is an open cover of R, right? Each each of this element, each of these intervals are open in R and they cover R. So this U is an open cover of R. Now, does it have a finite subcover?
No, ma'am.
No, because if we take a finite subcover, then there must be some n belongs to n such that R is contained in union of this n equals to 1 to n minus n to n, right, which is nothing but minus n to plus n, right. So R is contained in minus n to n. This is absurd, right? This is not true. So this is not true. So it does not have a finite subcover. So U does not have a finite subcover. Sorry, if there exists this, then so U does not have a finite subcover. So R is not compact because this cover does not have a finite subcover. Okay. Okay, now let's take another example. This open interval. This, suppose this y is 0, 1 and x is R. So R is not compact. Now is this subspace 0, 1 is it compact? It is not compact. So if we take this open cover, say 1 by n to n, 1, right, n belongs to n, natural number. So union of this open intervals covers 0, 0 y. So U is an open cover of y, right, but it does not have a finite subcover, right, because this is suppose 0, 1. So if it has a finite subcover, then this y must be contained in some union of n equals to 1 to n, 1 by n, 1, right. There must be some capital N. So then this may be 1 by n. So union of 1 by n, this covers actually from this 1 by n to 1, right, because all this n is less than n. So 1 by n is greater than 1 by n. So 1 by n is the smallest. So union of this is actually 1 by n to 1. So any number in between this, suppose 1 by 2n, 1 by 2n, it belongs to y, but 1 by 2n does not belongs to this union, right. So it does not cover, this finite subcover does not cover the whole y. So U does not have a finite subcover. Right? So 0, 1 is not compact. Now what about any space with discrete metric? So let's take X with D star, the discrete metric. So is it compact? It is bounded, right? Because distance between any 2 points here is 1. maximum 1, maybe 0 or 1. So it is always bounded, but is it compact? Now we know that any finite subset of a metric space is compact, right? So now, take X to be infinite. Now is it compact? So in discrete metric space, so take a open cover. So let's take A subset of X, right? And A is also infinite. Since X is infinite, I am taking any subset which is infinite, right? Now take an open cover of A. So U, which is the collection of singletons where A belongs to A, right? This is an open cover because the singletons are open in discrete metric space, right? So U is an open cover of A, right? Now this open cover does not have a finite subcover because any finite subcover of this U is actually finite and our A is infinite. So any finite subcover can never cover A. Okay? So it does not have a finite subcover.
Ma'am,
Yes?
ma'am, how do we choose open cover? Ma'am, what thing we should keep in mind in
Okay.
any question?
No, there is no any formula like this. You have to think of it, right? The more you solve the problems in exercise, then you will see a pattern. Okay, like in 0 1. In 0 1, you can take 0 1 minus 1 by n also, right? Then you will also see that this does not have a finite subcover. Here I have taken 1 by n 1. So there are many possibility, right? Not just this one. But for this you have to solve many problems. You have to read the books, the examples. Then you will see a pattern, right?
Okay, ma'am.
Okay, so here this U is an open cover of A, and any finite subcover of U is finite, right? So this means what? This means U, this means any finite subcover and finite and A is infinite, right? So U does not have a finite subcover of A. So U so this means A is not compact. And A was what? Infinite. So this means a discrete metric space X is compact if and only if X is finite, right? This means a discrete metric space is compact if and only if it is finite. It has to be finite. Finite means compact, right? Now a discrete metric space is compact means it has to be finite. It cannot be infinite. So it is an if and only condition. Okay. Okay. It is. Now we'll describe a result. It says every closed subset of a compact matrix space is compact. Every closed subset of a compact matrix space is compact. The proof is easy, but we don't have that time. So just take, so suppose y is a subset of x, right, xt, and y is closed, right. So you have to show that y is compact, right. So take an open cover u alpha. So u alpha, oh sorry, ub u alpha, okay, where alpha belongs to this lambda, where lambda can be arbitrary, okay. This is an open cover of y. I'll just quickly tell the proof. So it is an open cover of y, right. Now since y is closed, this x minus y is open, right. So this is suppose x, right, this is the whole x and this is y, right, and we have taken open covers of y. So this some, this is cover open sets, this is some u alpha, u alpha 1, u alpha 2, like this open covers of y. And this part is what, this part is x minus y, right, x minus y, and x minus y is open, okay. So now this set, this u alpha, alpha belongs to lambda, union x minus y, this covers x, right, and this is an open cover because u alphas are open and x minus y is also open. So this is an open cover of x, and our x is what, x is compact, the whole space x was compact, right. So this open cover has a finite subcover, and from that finite subcover you will find a finite subcover of y. So y will also be compact, right. You get it, right, this proof. So just write down the proof properly. So every closed set of a compact matrix space is compact, right. Okay, the next theorem says now compactness means closed and bounded in every matrix space, right. So this says a compact subset of a matrix space xt is closed and bounded. Right. I'm not going to the proof of this. So compactness means closed and bounded, right. Now is the converse true? Now the question is, so compact means closed and bounded, always closed plus bounded, right, this is true, this part. Now what about this part? If a matrix space is closed and bounded, does it mean it is compact? So this is not generally true. So we'll take this example. So take this example x. We have already seen this x with this star, this discrete metric. Discrete metric and x infinite. So you have already seen this one here, this one. What we have seen? We have seen that discrete metric space is compact if and only if it is finite. So infinite discrete metric space is not compact. So it is not compact, right? So this one is not compact. It is not compact, but it is closed and bounded. It is bounded, right? Bounded because distance between any 2 points is maximum 1. So it is bounded. So, and the whole space is always closed, or we can say yes, the whole space is closed. This whole space X is closed, right? Plus bounded, but it is not compact, right? Whole space is always open and closed. Phi and the whole space are always open set, means phi and the whole space are always closed and open. These are the only two closed and open sets. Not only two, maybe in discrete metric space every point is actually open and closed, every singletons. So every subset is actually open and closed, right? So if we take any subset here A, which is a subset of X, which is infinite, then this A is also closed. This A is closed, right? Because every subset of a discrete metric space is open as well as closed, right? Because closed means what? Closed means the open the whole space minus a open set, right? So every subset is closed, so it is closed plus bounded, but it is not compact, right? Okay, so I am going to write down the theorems, but you have to, yes,
There is a possibility of A is compact.
yes, here this xd star, yes,
Okay.
any finite subset is compact,
Yes.
but for infinite not no infinite set can be compact for discrete metric space, but finite set is always compact. Okay,
Okay.
okay. Now if we take a continuous function from a compact metric space, then the image will also be compact. Okay, this we have to prove, but so this is a theorem, I don't know, 5 maybe. So f is a mapping from x d1 to y d2. Okay, and f is say continuous, then if a is compact, then fa will be compact in y d2, right? You have to prove this because there is no time, it's already 9. And now the question is, if this property holds for every function, say for every that image of every compact set is compact, right? Now then the question is, does this mapping is continuous? So there is a map which sends every compact set to compact set. Okay, so the question is, this function is continuous or not, means converse of this theorem holds or not. So we see that converse of this theorem 5 is not true. Okay. So we'll see a function which sends compact set to compact sets, but it is not continuous, right? So take this function f from R to R, say RD to R D star. Okay, so this D star is D star is suppose discrete metric, right? And this D is any metric. Because we have to choose compact sets from the domain, right? So we don't need to take any metric in the domain space. So D can be any metric. So we are choosing D star, the codomain, to be discrete metric. Now image of every subset of R is I think I have chosen so we don't need to take metrics actually. It depends on the mapping. So take f from R to R, where this function fx is 0 if x belongs to rational number and 1 otherwise, means 1 if x belongs to irrational. Okay, this function. Okay, I am not choosing any metric here. So now if A is, so image of every compact set, every subset of R, so image will be always a subset of 0 and 1, right? Image of every subset of R is a subset of the finite set 0 1, right? Image of every set may be 0 1 or 0 1, right? So image of every set is a finite subset, is a subset of this 0 1, and this set 0 1 is compact and every subset of 0 1 is compact. So image of every compact subset is always compact, but this function f is not continuous, right? This is not continuous. So image of every compact set is compact, but f is not continuous, right? And we'll see that any continuous function from a metric space, from a compact metric space, is actually uniformly continuous. So this is also a theorem which you have to prove. Okay. If you have any doubt, then you will tell me, I can prove this in the next session. Okay. So this says any continuous function on a compact set, on a compact metric space X d1 to a metric space Y d2 is actually uniformly continuous. So these two theorem, this theorem 1 and theorem 2, you have to prove on your own. Okay, you can take help from the book, but this, the proof is necessary if you do on your own. Okay, so I'll end this session. So if you have any doubt, then you can ask. Okay, so I guess you don't have any doubts. Okay, so we'll see in the next session. Okay, so good night everyone.